Let's talk a little bit about mass versus weight. Okay, we got the blue pen going here. In chemistry class, I believe you use mass and weight interchangeably. In physics, they mean different things. Okay, mass is the amount of stuff. Weight is the force of gravity. Okay, mass is stuff. Weight is the force of gravity. Okay, so let's just drill down into that. Okay. Mass is the amount of stuff you have. So basically, if you have 12 grams of carbon, right? We know how many protons, neutrons, and electrons you have. This is amazing, right? Okay, you've got if you get 12, if you have carbon, right? Okay, carbon 12. You've got what, 6 moles of protons, 6 moles of neutrons, 6 moles of electrons. It's amazing to me that you could figure that out, right? Okay. Mass is measured in kilograms. It's also measured in grams. And then the English unit for mass is not a pound. That's actually a unit of force. Okay, like pounds of thrust on an engine, right? The English unit of mass is a slug. This is kind of fun, right? Okay. And in the Pacific Northwest, of course, we have a vivid mental image of this, right? And I'll give you this clue. A kilogram and a slug are quite different numbers, right? A kilogram is the amount of mass you have that if you exert a force of 1 Newton, right, it accelerates at 1 meter per second squared. Okay. A slug is how much stuff you have if you exert a pound of force, and it accelerates at 1 foot per second squared. Now, I'll give you these conversion factors, right? 1 foot per second squared. Oh, wait, hold on. Let's do it the other way. I don't know this way. 1 meter per second squared is equal to 3.281 feet per second squared. Okay, and 1 pound is equal to 4.45 newtons. So think about this, right? You exert about 1/4 of a pound on this object, and it accelerates at like 3 times as fast as this. Here you exert 4 times as much force, and it accelerates much more slowly. So here's the question: which one's bigger, and what's the conversion factor? I'll let you guys puzzle about that. Okay. All right. Let's hit the right arrow. It's mass is a measure of inertia. The more mass you have, obviously, the more inertia you have, and you would have that in space, right? If I've got a kilogram of iron, I've got this on Earth, I've got it in space. It's the same thing. The amount of stuff I've got is invariant. It doesn't matter where I am. Okay, mass is definitely not zero in space. Okay, you can be weightless, but you can't be massless. Okay, just saying. Okay, the only things that can be massless are things like beauty and truth and stuff like that, right? Although I would argue that beauty and truth are concepts, and if they exist, people think about them, and thinking is energy, and energy has mass. But I'm just a scientist, not a poet. All right, so wait, well, watch this animation. Whoa, it comes down, right? I won PowerPoint of the Year in like 2004 for that animation. That, it was a pretty desperate year, really. Okay, weight is the force of gravity acting on an object. It's measured in newtons. It is also measured in dynes, and a dyne is the amount of force you need to accelerate 1 gram at 1 centimeter per second squared. So you tell me which one's bigger, a newton, which is a force that accelerates a whole kilogram at 1 meter per second squared, or a dyne. Okay, I just put that there in case you were dying to know. All right, and then a pound is actually a unit of force. It's weight. Okay. I weigh 170 pounds on Earth. I weigh 0 pounds on the moon. Okay. If you are not in a gravity field, you don't have any weight. That's fun. Or if you're accelerating in the direction of a gravity field, then you also don't have any weight. This could be in orbit. You could be in orbit. We could be dropping you, right? Okay. And then the demo calculation here. Let me just show you this. Okay. The force of gravity, or the weight, is equal to just mg, right? And g is the gravitational field strength. So on Earth, g is equal to 9.81 newtons per kilogram, okay? And notice how we said it was, and we just used 9.8 in regular physics. Notice how we said it was meters per second squared. Well, a Newton per kilogram is the same thing as a meter per second squared. But really G is just how strong gravity is. And if you go significantly farther from the surface of the Earth than we are now, it actually drops off a little bit. So let's do an example. Okay, if you have 5 kilograms, that's its mass. Okay, its weight is the force of gravity is just, and notice this formula is just mass times the acceleration of gravity. That's one way to think about it, right? So that's equal to 5 times 9.8, right? Which is 49 newtons. Okay, so this is its mass. It has this mass on the moon. It's got this mass on Mars. If you took it on the space station, it would have that mass. Anywhere you take it, it's that much mass. If it's iron, that's so many moles of iron. It's so many protons and neutrons. That's invariant. That doesn't change. On Earth, there happens to be a force of gravity acting down on this mass of 49 newtons. On the moon, it would be less. On Jupiter, it would be more if it had a surface, right? Okay, so just keep that in mind, okay? That's the difference between mass and weight. Weight is force of gravity. Mass is just stuff, okay? Related to moles, for example. All right.